Today we're looking at exponential equations, and we're dealing with exponential equations that have the same base. The reason why we want exponential functions that have the same base, because if we have exponentials that have the same base, just creating one off the top of my head here, what we can do is cancel these two bases. Since it is the same math, just like multiplying by 2 or dividing by 2, if these two numbers have the same base and they're equal to each other, that means their exponents have to be equal to one another. So I did a very basic example there, but if we can get these to match, we can do this. What I want to make sure that we understand right off the bat is the bases have to match identically. Even if you recognize, well, these numbers are 4, here's a common mistake people want to do, is they want to treat it like this is multiplication and say, well, that's a common factor, so I'm going to mark these down to. That's not at all how these work. That is a very crucial mistake. Make sure that you do not make them. Either the bases are identical or we cannot do anything with them. We are going to learn how we can reduce the bases. I actually have a calculator method I'm going to show you as we do these as well. Very important you catch these. If you haven't logged on to your Delta Math, go ahead and do that. This is our Delta Math assignment. We'll follow right through all of those examples. All right, so today what we're going to take a look at is graphing these logarithmic and exponential functions. Today we'll only look at the logarithmic function. Need our calculator to do this, so let's go ahead and take a look. We notice our formula is log base, or 3 log base 5. So remember, log base is under alpha F2, and there's our 5th option. So this is log base 5 on. Notice the x is not in a parentheses with the 6, so the x should be the only one that's in my parentheses. And then we go minus 6. So if we think about this, remember logarithms are the functions that generally hit the y-axis and drop immediately. So this one has been shifted down 6 units, so it's probably still going to go on that. And there you can clearly see that's what we have. So we do have an asymptote here, and it is a vertical asymptote. And then we're going to set this vertical asymptote up at the y-axis, just like you see me doing there. Now we've got to plot 2 points on this function. We can see these are both below. So what I'm going to do is, again, go back to my table. See if I can get that bigger screen pulled up here. So I'm going to go back to my table and hit second table and find 2 points that are easy to graph. Like 1, -6 is clearly very easy to graph. So I'm going to plot 1 point at 1, -6 right there. Zoom in and help yourself out a little bit. And then as I look through the table, I can also see that there is another clear point at 5, -3. So I'm just going to pull my cursor right there to 5, -3. And then I'm set. I'm going to just take another peek though, make sure that my graph actually looks like what we see there. And then you could even look, you saw another point. We saw another point was at, maybe we didn't see it. I'm sorry. So these are the points we have, and we should be good with this bit of information. So I want you to get accustomed to, one, typing these in, but secondly, I want you to be able to look at your table and determine what's happening. And you'll also see the asymptote. Remember, vertical asymptote, straight up and down. Horizontal is left or right. Horizontals are the ones that will show up when you have an exponential function. So we are asked to solve this equation here. You don't have to get it to the smallest base. If you recognize a base that they both share, you want to get it to that base. For instance, 16 is equal to 4 squared. That would get us to a common base. So here's what I'm going to do. I'm going to change my 16 into 4 squared. That is 16 right there. What we need to understand is when we change this number, The exponent that we created, in this case that was 2, joins the exponent that was currently there. So this is going to be 4 to the 2x power. Now we don't really want to touch the other side because now we have a common base. There was actually a common base 2 we could have adjusted, but as soon as we find a common base between the two numbers, we can cancel those two out, just like you see me do there. I'm going to back up just a second. That's why we want to aim for that common base. Because if it's 4 to some power is equal to 4 to another power, that means those two numbers have to be equal to one another. So once we cancel that base 4, we have 2x is equal to 3x minus 1. And from there, we're just going to solve for x. So I move the 2x over to the 3, and I'm going to add the 1 to the side that currently has nothing. So 0 plus 1, of course, is 1. So this is how we solve our exponential equations, excuse me. What I'm going to show you is how we can use a calculator to help us find a common base on these very unfamiliar numbers. We want to get a common base so that we can cancel it. So we're going to check out the number 7,776 and 216. So what I'm going to do is I'm going to go to my y equals, and I'm going to type in this. If I hit math, and then if you notice the fifth option is to an unknown root. So I'm going to hit this, and I'm actually going to use the variable button here. So I'm looking for any root that I can find where 7,776 will work. Now 216 is also a number I'm interested in. So I'm going to do the same thing. Option 5. Unknown root, because I don't know what it is, and I want to have the highest one I can get, and then I do 216. Now this is going to be a little different than we're accustomed to seeing. What we're accustomed to seeing is looking through the x values, but what we're going to do is look for the y values. So I go to my table, and I want to see a y value that they both share, and I want to take the highest one that they have. So I can see 1 and 76, obviously 1, the first root, but as I look, I see that y2, the second one, has a 6, and the y1 also has a 6. So these two actually only share one common root, and that's the 6th root. If I had more than one root, which some of these will, I'll take the highest root that I can get. So what I've learned from this is, since this has a base, this number has a base of 6, and it is 6 to the 5th power because of our information here. And then the y2 number, the smaller number, 216, is y to the 3rd power. So we can use our calculator to help us to find the most efficient roots as we move through these. So since we've learned that we'll highlight this, 7,776 is equal to 6 to the 5th power. This is actually going to have to join the top with a parentheses here. I'll zoom in a little bit while we do these. So those add to those values there, and then 216 was 6 to the 3rd power. It's very important that we drop some parentheses up here to join these two exponents. So what we have is 7,776 is 6 to the 5th power, just as 216 is 6 to the 3rd power. But since I've matched those since I've matched those base values, I can cross the base values out, and I essentially have a linear equation. So I have 5 times 2x plus 1 is equal to 3 times 3x minus 2. Some of you probably would have preferred to distribute those before moving those down. It really doesn't matter. Just make sure that you perform all the operations that are supposed to happen. So this becomes 10x plus 5. 3 times 3x is 9x minus 6. So I'm going to move the 9x to join the 10x, which gives me 1x. At the same time, I'm going to move the 5 away since I'm moving the x's to the left. So negative 6 minus 5 equals negative 11. All right, so as we look at this next example, we have really just bigger numbers, but if we're using the calculator trick, our y equals the xth root of 3125, and then the y2 being the xth root of 625. And if I look through my tables, there's actually only one set of integers that these even have. So it is the number 5. And what I learn is that this is equal to 5 to the 5th power, and 625 is equal to 5 to the 4th power. I'm going to highlight this for you. This is this. This is this. Now everything else is just going to come down as the powers that they are, with a parentheses though. Got to remind myself that I am multiplying, so this is negative 4x plus 8. So once I've established a common base, I can cancel that common base. So those are going away. And in the top, again, I told you on the last one we can distribute before we move or after. It does not matter. If you distribute right there, that's fine and good. I'm going to go ahead and show every step though. But some of you, that might be a really good move. So there we have that. Obviously, we have distribution. So we're going to distribute our values in. That would be negative 20x. This is going to be positive 25. On the other side, we have 4 times negative 4, negative 16x, and then 4 times 8, which is 32. Now, whenever I'm solving an equation, I like to make the smaller variable go to where the bigger one is. Well, in this case, negative 20 is a negative number, so it is smaller. So I'm going to move the negative 20 over to the negative 16. And the reason why I choose to do it this way is because I'll never have to divide by a negative number if I do it this way. Since I chose to move the variables to the right, the non-variables like 32 have to be moved to the left. So I subtract the 32 over here, and that gives me negative 7. So 4x equals negative 7, so I divide by 4, and I learned that x is equal to negative 7/4. So if we can find those bases, these exponential functions are really linear equations for the most part. We can get into some more difficult ones, obviously, but once we get past that common base, we're ready to move. So this one is one of the more difficult ones, and it really isn't if you really kind of get the idea of what we're doing with the graphing calculator. If I were to go into Y1 and type these numbers in, just like we've done on the last questions, 1 over 32,768, and then my Y2 is equal to xth root of 1 over 4,096. So when I put these in my calculator, what you've got to pay attention to is whenever we have these really small fractional numbers, write this down, a little note to yourself. When you have these fractional numbers, especially 1 over some other thing, you're about to have a negative exponent. you're about to have yourself a negative exponent. So it's very important as we look at these things that we know where to look in the table. Remember, the base numbers are whole numbers. We're still looking for those. Now, I'm looking at my table now. I have my calculator in my hand. Hopefully you have the same. So when I look at the table, my x and y values, when I'm looking at my positive values, I don't really have anything very useful. It gives me a bunch of fractional numbers and I'm not seeing anything. But if I back up in my x's and look in the negative signs, I have several different options actually that I can use. And what I learn is in one of my sides, it's -5, 8. This one came from my y1. And my y2, this is a totally different section here. We'll divide it this way. It has an ordered pair of -4, 8. And remember, the whole purpose of using the calculator is actually to make the y's match. So what I've learned is that this number, 1/32,768, what it is equal to is 8 to the -5 power. Highlight this for you, make sure we're understanding what happened there, because it looks very funny. It's hard to get used to that, but that is 8 to the -5 power. And in my other one, since I have the -4, 8, it has a base of 8 as well, and it has a -4 power. This is this. So my point is, make sure, especially in these fractional numbers, that you check those negative ones as well, because the negative functions are going to give us these weird fractional values. Because remember, it's not multiplication, it's an exponent. So a negative power means the inverse of. All right, so we're going to carry down the exponents from before, 5x minus 10 and -3x plus 13, just like you see there. So we match the base values. So since we've matched the bases, we can cancel those. Now, if you had a lower number that matched, you could use it, but you're going to be distributing a larger number. I mean, it's not a real big deal, but it's just a little more effort than you would have to use if you chose the higher base. So now I've gotten rid of those bases, and I'm back to a nice little linear equation. And with that, I'm going to distribute -5 into each of those terms. Be -25x plus 50 and -4 times -3 is +12. -4 times 13 is -52. Again, I like to make the smaller variable go to the larger one. Well, in this case, -25 is smaller than 12. So I move it with addition. So this would be 37x. Since I move the variables to the right side, the non-variables are going to go to the left side. So I add 52. This equals 102. So the final step here is to divide by 37. And we learn that x is equal to 102 over 37. And that number actually does not reduce any further. So that's going to be our answer. All right, you've got some examples to work on your own. Make sure you understand how to get a common base with your calculator. If you want me to show you how to do this by hand, I'll do that. but it's a little bit of a mess. You can use your factoring tree to figure these things out, but your calculator is just much faster, probably more efficient as well. Good luck.